Oh, that was nice. Do it again.
Riding on a big white butterfly, I turn my back away towards the sky. Close my eyes to look for something, so myself is really nothing. Then I realized my butterfly wasn't really up there with me. We all make mistakes, forgive me. Would you like to ride my butterfly? Riding on a long blue paper plane, getting seasick, sorry once again. Landing strip is getting near, hope the fog lifts, make it clear. Then I realized my paper plane wasn't really up there with me. We all make mistakes, forgive me. Would you like to ride my paper plane? Riding in a 3 grand Deutsche car, A to B is often very far. Home is near but such a long way. Legs and heads all feel the wrong way. Then I realized my Deutsche car is only there to get me somewhere. Even so, I really do care. Would you like to ride my Deutsche car? Would you like to ride my paper plane? Would you like to ride my paper plane? Would you like to ride my paper plane?
All right, so today what we're going to do is we're going to transition over into object-oriented programming in Java. And we've already touched a little bit on it by designing a class to represent books and people, and then using that to do some data processing. But what I want to do at the top of object-oriented programming is go through another problem. Because what I want to do is I want to solve this problem using what are called structural programming techniques. So the programming techniques that you've been using in C and Java up to this point is called imperative style. Now, the imperative style is you've got a command 1, then command 2, then command 3. Maybe you've got a loop that iterates over that loop several times. Maybe you've got an if-else-if statement and branches out. But that's all structural, or it's all imperative paradigm where you're telling the computer exactly what to do. Object-oriented programming is a little bit fundamentally different design in that, remember, it's a bottom-up, right? We're going to design our objects first and see how they interact with each other. So let's just go ahead and get into it with this physics problem, right? Now, you don't have to know any physics or how it works. You just have to know this is enough of a primer right here. That if you've got a radioactive isotope of an element, that means it's radioactive. It gives off radiation, alpha decay, beta decay, whatever, and it will have a half-life of some measure, right? So, for example, strontium-90, which is a byproduct of nuclear fission, so nuclear explosions, has a half-life of 28.9 years. Meaning that if you started out with 10 kilograms of strontium-90, then 28.9 years later, approximately 29 years later, you would only have a half, like 5 kilograms instead. And now the rest of it didn't just evaporate. What it did is it decayed into uridium and zirconium, right? Two other radioactive isotopes. Those will decay some half-life into other isotopes. Those will decay into other isotopes until it gets down to a stable element, right? And which is not an isotope anymore. It's just a stable element. It doesn't give off radiation anymore, right? So, for example, we're going to write a program that reads in some data about an isotope. I'll actually simplify it. We'll just read in the name, the half-life of the element, and an initial mass in grams or kilograms, whatever you want, right? And then what we'll do is we'll formulate this table that if you start out with 10 grams or 10 kilograms or whatever, right, after the first year, you would expect to have only 9.76 grams because it is decayed by this amount right here, right, where you've got the number of years, so the first year, 1, divided by the half-life, 28.9 in this case, and then you raise 1/2 to that power, right? That's why it's called half-life, it's 1/2, right? And then times that original mass. After the second year, you will only have about 9.53 grams, ... After 29 years, you will have less than half of the original mass. In this case, 4.99 grams are remaining after 29 years, right? So let's go ahead and solve this problem over here in Eclipse using Java, using an imperative style, right? So I'm going to go ahead and create a new project to do this, just as a review, right? So if we still need to create a project here, I'll go ahead and go with assignment. I don't know. I'll call this assignment 0. I already have something like that, so I'll call this assignment 0 with ECE. Another note here, I didn't mention it before, but it won't be relevant for the first assignment because you can turn in, you're not going to be using any like advanced Java stuff from Java 22 or 23, but you should use Java 21 in your project because the grader server, the Neuros grade server that we use only has Java 21. I'll put in a ticket for them to upgrade, but I don't know when they'll be able to get to it, okay? The other thing to note here, remember that you do not want a module system, right? So make sure that this is unchecked. You'll run into problems later on if you have that checked. But otherwise, you organize your code in the source package. I'm going to create a new package here. And I'm going to use the same package that we've been using for everything else, UNL SOC, right? And remember, do not create a package info Java file, right? Get rid of that, okay? So I'm going to create a new class, and I'm just going to call this isotope demo, right? And we're going to solve this in just one function here, main. Public static void main string args. Right? Now, like I said, we're going to simplify this program so that we're reading in a name, the name of the isotope, strontium-90. We're going to read in the half-life, which is going to be a double half-life. Life in years, of course, and finally we're going to read in initial mass, right? Okay. Good variable names because they label what they are, right? And if you've got multiple words like half-life, you don't hyphenate it because that would not be syntactically allowable. Instead, you use lower camel casing. Right? Likewise, initial mass. Okay. Now I'm going to read these in as command line arguments, meaning that I'm going to be reading in args up here. The first thing I should do is check to see if there are enough arguments. If args.length, how many arguments am I expecting here? 1, 2, 3. Right? So if args.length is not equal to 3, then I should issue an error message. Right? System.out.println error. Specify name, half-life, and mass. Right, that's good enough. Right? And in fact, an improvement here, instead of going to the standard output, I could go to the standard error. And then it'll print to the standard error, and the only difference here in Eclipse is that it'll be red down here. Okay? And then, is there a reasonable way to recover from this? Like, are there defaults? Is there a default isotope or a default half-life? No. So what I'm going to do is I'm going to exit on them. Exit 1. Right? With an error code of 1. Okay? Now, if I ran this right now, I'm not providing any command line inputs. Remember, remind me, how do you do command line arguments? The play button, run configurations, and let's give it arguments. Strontium 90, right? And its half-life was 28.9 years. And we'll go ahead and start out with 10 grams, okay? Just like in the handout. Apply that and run it, and there we go. No news is good news because, of course, we haven't completed our program yet. How do I convert these three items over from the command line arguments? Well, the first argument is going to be args of 0. Do I need to convert a string to a string? Remember, these are all strings, so I don't need to convert that. What about args of 1? How do I convert a string into a double? Double dot parse double, parse double, and then args sub 1. Okay? And copy paste that because we're going to do it for the initial mass as well. Args of 2. Okay? Now you can do some basic error checking here. For example, does it make sense to have a negative half-life? No. Does it make sense to have a negative mass? No, that doesn't make any sense. So you can go ahead and check for those stuff. If half-life is less than 0, right? Or initial mass is less than 0, then we can issue a different error message. Right? Not that you necessarily do need to do that on your assignment, but just for completeness here. Right? Error, half-life, and initial mass cannot be 0. Be negative, sorry. Right. There we go. And we'll exit on them with maybe a different error code, 2. Right? That's why error codes exist, so that you can issue an error code of a different type. Right? Something happened of type 1, something happened of type 2. Right? All right, so again, that's not absolutely necessary, but we'll go ahead and do that just for completeness. Okay? Now what I want to do is I want to produce a table that looks something like this. Okay? Now I have not read in the atomic number or the atomic symbol because I just simplified that. But let's go ahead and output the values that we do have here, right? As well as this header up here. Right? So system.out.printf, say, %s is going to be our name, right? Name. And then let's also output the half-life and the initial, we don't need to output the initial mass because that's in our table. So the half-life is going to be, say, 0.2f years, right? And half-life. There we go. And then I want something that looks like this, elapsed years with that. In fact, I'm just going to cut and paste that because I'm going to steal that. And system.out.printf, printf, there we go. Elapsed years, there we go. And then steal this code right here to align it right here, right? And that one. Are we good so far still? And then finally this one right here, right? And then here's our initial mass. I'll go with out to 2 decimal places. Two decimal places of accuracy there. Initial mass. Okay. Now if I run this, I'll of course get that first. Oops, sorry, we should go next line there. We'll get that header right there. Right? Okay. Now we need the rest of this table here. Right? In other words, we're going to have to decay our element until we get down to less than half of the original initial mass. Ideas on how to go about doing that? Yeah. Okay, so we know what the half-life is, right? 28.9 years. So we could just, sealing that or round that up, right? And then that would be the number of iterations that we want to go. Sure. How would we do it with a while loop instead?
Like while the mass is still above a certain price.
Is still above what?
Like half of the original value.
So 0.5 of the initial mass. Okay. I like that. But do we have this variable mass here? Nope, so let's go ahead and create that variable mass here. Why is it different than initial mass? Right? The initial mass doesn't change, right? We started out with 10, right? And we need it in our loop control structure over here, right? But while that current mass, in fact, you could call this current mass if you wanted to, but while that current mass is greater than or maybe equal to, right? Because we want to know when we get down below it, right? So as long as that current mass is greater than 1/2 of the original mass, the initial mass, right? Then what do I need to do? I need to decay the mass by 1 year, right? And also in this table, I'm going to want to keep track of the number of years. So maybe a for loop would have helped me do that. But let's go ahead and put it into another variable. And here it is going to be a whole number, so I'll start out year 1. Okay? Decay the mass by 1 year and increment year. Well, that one's easy enough. How do I increment year by 1? Year plus plus. There we go. How do I decay the mass by 1 year? That is this formula right here. All I need to do is take the mass, multiply it by 1/2, raised to the power of the number of years, so 1 year, divided by the half-life. Right? How do we do that math, by the way? Math dot pow, 0.5 raised to 1 divided by the half-life. Right? That expression right there is this thing right here. But now I need to multiply it by the mass. Okay? So the mass is equal or times that. Right? That will reduce the mass by not by 1/2, right? But by 1/2 raised to the small amount. Okay. So I need to update this mass to be that mass. Right? So there's some considerations here. First of all, whenever you're doing division in C or Java, you have to be careful. Because what is 1 divided by 10 in both languages? 0 because of integer truncation. Do we risk integer truncation here? We do with 1, but what about half-life? That's a double. We're good. Right? Still, if you're paranoid, go ahead and put a 0.0 there. Right? And now you're good. Is there a better way to update this? Plus equals, or multiply equals? Yeah, multiply equals. There we go. So we could multiply equals. Oh, sorry, multiply equals. Okay. And then of course I need to output the mass, right? Where would I do that? Would I do it here? System.out.printf %d and then I don't know, a whole bunch of spaces. %d is going to be for the year, a whole bunch of spaces, and then %.2fg. G there is for the grams, right? And then end the line. I'm going to output years, or year, and then the mass, okay? So what if I were to do it here? Predict. What is the table going to look like? Remember, I already printed out the initial mass before the first year. This is going to print out year 1, but then is the mass changed at all? Nope. So it's still going to be 10 in that. I should end the line right there, sorry. And let's look at it again. Right. So 10, 10. That's not right. Right. So I don't want to output it first thing. Do I want to output it last thing? Right. Remember, this is the tricky part of while loops. While loops, you can do the things in any order, right? And it might be off by 1. Right? Well, that looks good, kind of. So 10, and then after the second year, we're down to 9.76. We're down to 9.76 after the first year, but now our years are off by 1. So where should I put this print statement? I tried putting it at the beginning. I tried putting it at the end. I should try putting it in the middle, right? There we go. And now let's see if this works. 1, 9.7, and then all the way down to 29, 4.99 grams remain. Okay? Good. Some good practice. Go ahead and make sure that you format everything up. I would turn, by the way, this is going to lose some points. Why? I need to have at least an author header here. I wrote it, yay, for me, 2024, 02, and what is today, the 6th? There we go. And also you need the purpose of the program. This program generates an isotope decay table, right? That's all you need, right? Just describe it a little bit, okay? All right, otherwise, you'll also would have points deducted here and here because that's cruft, right? I put that in there to outline my program, but once my program is done, that stuff should be eliminated, right? Extraneous comments should be eliminated. I will go ahead and preserve it in case you want to see it in the notes, okay? But otherwise, that is a 100% probably right there, right? That was not object-oriented programming, right? Were there any objects here at all? Nope. Not like there were over in our original demonstration with books. We had something to represent a book. We had something to represent an author. Where is an opportunity here to define an object? What are we modeling? What are we talking about? Talking about isotopes, right? Now, why would we want to define that object? We have multiple pieces of data that define what an isotope is. What are those pieces of data? The name, the half-life, and the initial mass, or the mass. We'll just call it the mass. So, instead of doing what we just did, what we should have done from an object-oriented programming perspective is first define an object. That's going to be a class, isotope, okay? There's not going to be a main in here because initially what we want is for it to, the first step in designing a class is to ask yourself, what is the state of that class? What are the variables that go into that class? Well, it's pretty straightforward here. These three things, right? Half-life, mass, and name. Right? So let me grab those just as a reminder over here. And I'm going to have private string name, private double half-life, right? Private double mass. Right? Now I can get rid of that stuff. Okay? Why did I make everything private? Because I want to protect those variables. I don't want the outside world to see them. If you want the outside world to change them, fine, go ahead and develop setters for them, right? Remember, create, retrieve, update, and destroy. I need a way to create an isotope. And that means that we are going to create a constructor. Right? So there's a constructor. I didn't have to type a single thing. You give me the name, the half-life, and the EMAS. I don't know why I called it EMAS, but whatever. All right. There. All right. Mass, not EMAS. All right. There's a constructor that takes those three things. Right? You do not need to document this. Right? You can if you want to, but it is a constructor. It is a trivial method. Right? Once you know what constructors are and how they work, you don't need documentation on it. It's a constructor. It is self-documenting. Right? If I were to write a piece of code saying int a is equal to b plus 42, and I'll creates a new variable called a and sets it to a value equal to b plus the value 42. Plus in this case means addition. Would you ever write something like that? I just wrote like 10 times as many characters as the code takes up, right? Don't do that, right? That's cruft, right? That code right there is self-documenting. It takes the variable b, adds 42 to it, and puts in the variable a, right? Okay? This code is self-documenting. What you should do, however, is document your classes. Represents a radioactive isotope. Okay? And then you could put a link in there to Wikipedia on radioactive isotopes if you want to. You do not need to go that far. All right, create, retrieve, update, destroy. C is done, right? Remember that, CRUD. Create, retrieve, update, destroy. So let's go ahead and check mark each one of these. Do I have a way to create something? Yeah, that's the constructor. Do I have a way to retrieve the data stored in this object? Not yet. So let's do that. Let's generate the getters. I'm just going to generate the getters, right? So that if you ever want the name of this isotope, you can get it. If you ever want the half-life of this isotope, you can get it. If you ever want the mass of this isotope, you can get it. Okay? No, you do not need to document those either. There's trivial functions. They get you that data that's labeled right there, right? Okay? That's a retrieve. Actually, before we do that, I'll go 1/2, right? Another way of retrieving something is let's see, toString method here. Right? And we don't care, maybe we don't care about the mass, we just care about the name and the half-life. Just like we did over here when I printed this out, I want this formatting right here. So what I'm going to do is I'm going to steal that formatting and use it. String.format, that formatting, and then let's get rid of all of this. This dot name and this dot half-life is what I want to print out. Okay? All right. String.format, remember that that's the same thing as sprintf. Did you use that in C? Where you're printing not to the standard output, but you're printing to a string. That's the same thing right here. You're returning a string value that is formatted using this format. Otherwise, it's printf. Right? It's printf style formatting. We're going to format the name, and then we're going to format the half-life right here. Okay? All right. I would say that retrieve is done. What about update? Question mark, question mark. Do we want setters? Let me show you what it would look like. Do we want a way to change this isotope's name? Oh, now it's not strontium anymore. Now it's uridium. Maybe you do, right? I don't know. We'll come back to that. What about destroy? In C, you destroy something by, well, you create something by calling malloc, right? You initialize some memory. What do you do when you're done using it to clean it up, to destroy it? What's the opposite of malloc? You use malloc, right? Okay. You no longer, you need it, so you give it back to the operating system by freeing it up. So free, right? Is there a free here? Not in Java. Java has automated garbage collection. There is no destroy. It is irrelevant. It takes care of event. Irrelevant. There we go. Ant. Right? So it's irrelevant because Java takes care of all those details for you. Okay? All right. So I'll leave that for now. And now that we've got this data object, and it's just data, right? It's just holding these three pieces of data. You can retrieve these pieces of data. You can print these pieces of data out, and that's it. It's just a data object. Right? What I want to do now is come over here and modify my program so that I'm using that. Right? We're going to iteratively change this so it's more object-oriented, more object-oriented, more object-oriented. All right? So once I've got those three things, I can put it into an isotope. Right? And I'll just call it isotope. Right? Is equal to new isotope of name, half-life, and initial mass. Right? Okay? It seems, at least the way that it is right now, it seems like this is a stupid exercise. We've got the three variables already. Why don't we just do the program, right? Why is it necessary to create this object that holds those three pieces of data together? And we'll understand that here in a little bit as we redesign this thing, okay? All right, so there's the initial mass is already stored in the isotope. The year there, we'll go ahead and keep that. I'm going to go ahead and get rid of this just so that we have simpler code, right? But there, here's the first line that actually gets replaced, right? There's a lot of details here on how to format your isotope. How can I make this code simpler now that I've got a toString method? %s. Now instead of using, actually here's another way of doing it. Isotope.getName, right? Isotope.get half-life. Right? That's not very object-oriented programming to me. Basically what I've done is I've taken this data and I've put it into this object. just so that I can pull it back out of the object so I can print these two pieces of data together. A better way of doing this would be to simply let the object do all the work for you. Isn't that simpler code? And let's run, I'm not going to be able to run it because it's not compiling, but let's go ahead and get rid of the rest of this here for a second and see that it actually works. All right, 28.90 years. That is much better because now who's responsible for formatting an isotope so that it can be printed to the standard output? Who? Is it the isotope demo class or is it the isotope class with its toString method? It's the isotope class, right? Book things belong in the book class. Person things belong in the person class. Isotope things belong in the isotope class, right? And so we're going to now change the rest of the program with that principle in mind. I'll go ahead and keep initial mass if we want to, right? No changes there. But now let's go ahead and go down here and understand what needs to change here. Right? All right. I no longer have a variable called mass because the mass is stored in the isotope class. Mass is an isotope thing, so it belongs in the isotope class. So I'll say isotope.getMass. Right? While that is greater than or equal to half of the original mass, right, I will decay that mass by 1 year. Right? And I don't have mass anymore, so what I need to do is I need to change it to this. Right? Times, right? And then isotope.mass is equal to that thing. In other words, I need to update the isotope's mass to this decayed product. It's not letting me compile. Why? Can I change isotope's mass? The field isotope mass is not visible. Why? Because I made it private. Is that now an argument to make it public? Maybe. Let's come back over here and look at the consequences of that. Isotope.mass is equal to negative 45. Can you have negative 45 grams of something? No, that's not physically possible, right? Now, in the you can have like negative 45 grams of weight, right? Something that has negative weight, well, no, that would be anti-gravity, right? It has buoyancy, right? I was thinking of a balloon or something, but that has buoyancy in the atmosphere. It still has the same amount of mass, right? All right, so we agree that this is a bad idea, right? Let's look at an alternative. I'm going to make this private again, and I am going to go back and add that update, that setter. I'm going to generate setter, but not for everything because I don't want to change the half-life. I don't want to change the name. I just want to be able to set the mass. You give me a new mass and I will go ahead and set this mass. Okay. That means I can say isotope.setMass to this thing right here. Okay. A little bit better. Let's see if we broke anything, by the way. Oh, and this was isotope.getMass right here. .getMass. Okay. And run it. Did I change the program functionality at all? Nope, I just changed the design. Right? Sometimes this is known as refactoring. You have a working program, right? But the code base is mess. It's what's called spaghetti code, right? Because it's all a mismatch of disorganized code. So you go back and you fix the code, but you don't want to change it because you don't want to break it. It works, right? And it ain't broke, don't fix it, right? Sometimes you have to fix it because it's not maintainable. Yeah?
Would it be, if you're a programmer, would it be better to make a function or a method that basically does this whole model, or maybe you put it, you want to check the amount of grams after shutdown years?
Yeah, so
Would
what?
that be considered better programming?
I would say that we'll get to that, and we're going to improve this a little bit more. But you could argue that this one line, that's complicated enough that it should be put somewhere else, right? But as far as the loop goes, probably not. I mean, you're going to have to put the loop somewhere. If you put it in another function, then fine, but it's got to go somewhere, right? All right, so we didn't change the program at all. Right? This is still not ideal though. Right? What am I doing here? Like, let me read what I'm doing. Get the isotope's mass and multiply it by this thing over here. Right? And remember that this half-life over here, that is also, get half-life, that is also in the class. Right? And there, that we're good there. Right? So what I'm doing is I've got this isotope. It's an object that contains these three things. I'm going to rip it open and pull out the mass. I'm going to rip it open and pull out the half-life so that I can give it to somebody else, this function right here, or this line right here in this class, so that it can compute a new mass. Right? Then once I've got that new mass, I'm going to put it back into the object. Why are you breaking that object open just to do all of that? Just to shove something back in? Decaying by 1 year sounds to me like an isotope thing, right? So if it's an isotope thing, where does it belong? In the object, in the isotope class. Just remember that. It's an X thing. Where does it belong? In the X class, right? Fill in the blank for that. So I'm going to go back over to the isotope here, and I'm not going to want to set the mass anymore. What I want is a function, public void decay, right? Because that's what it's doing. It decays that this isotope by so much, right? So it decays this isotope by the given number of years, right? Okay. So for that reason, I'm going to have to pass in a years here. Right? I just want to do it for 1 year, but what if you wanted to do it? How much do we have after 5 years? How much do we have after 2 years and 6 months? Right? So, should this be an integer? 2 years, 6 months, can you do that? If it's an integer? 2.5 years? What should this be?
Could we make it another object?
Ah, okay. I was so initially, well, what about a double? Like 1.5 years. That's 1 year and 6 months. But what if I just took this away? Double X. X what? What are the units of that thing? Right? Is it months? Is it years? Is it seconds? Right? So I want another concept here. A concept called duration or period. Right? I'm going to call it period for the given period. Oops, home row, period. Right? All right, so I don't have I'm going to have to create this object. Remember, what's the first question you ask yourself in engineering when you're problem solving? Has somebody else already solved this problem? And yes, they have. There is a period defined in the Java time library. Right? That period can be years, months, days, something like that. Okay. Now, we are going to have to mess around with it here shortly, but at least we have this object here. Okay. That's even better because why? What is this period? Is it days? Is it months? Is it years? Yes, it's all of those things. It's a concept of a period of time. Right? That's much better. Now let's go, I'm going to grab this code over here and modify it. So this dot mass is equal to this dot mass times all of this stuff. Right? And then I'll say this dot half-life. And instead of 1 year, what is it now? Years. Right? I need to get years out of this period. And here is how we're going to have to do that. Unfortunately, it's not a clean way of doing it, but double years is equal to period dot get years. Right? Double, actually years plus equals period dot get months times how many, actually, get months divided by 12. We'll do it that way. This is only going to be an estimate, by the way, right? Actually, yeah, I'll leave it like that for a second. Years plus equals period dot get days divided by 365.25. Right? Okay. Now, why did I do double years here? Because, of course, you want to support 1.5 years. The way that period works in the time library is it keeps track of years, months, and days. Right? Unfortunately, months is kind of how many months are in a day? I'll ask that. Or how many days are in a month? I'll ask that. 28, 29, 30, 31? Yes, right? So unfortunately, it's not exact, right? If you want to tie this to a calendar, what you can say is today plus 5 months. That gives you another time. That gives you a time interval, and then another time, exact time 5 months from now, right? Unfortunately, this is going to be just to be an estimate where I divide it by 12, and then however many days there are, that's a fraction of a year there, right? Are we all agreed that this is at least a good estimate of a year's, right? Okay. All right. So, and then I've got too many parentheses there, right? All right, I'm not going to return anything yet, okay? We might come back and return something, right? But let's come back over here and see how this improves now, right? I'll leave that for a second. First of all, I need a period of 1 year. Period 1 year is equal to period dot of 1 year, 0 months, 0 days. This is how you use it in Java, right? Okay? There's my 1 year. Now, instead of doing all the math right here, I'm just simply going to say, hey, isotope, decay yourself by 1 year. That's more readable. That's way better design. Because that complicated stuff of that this half-life formula here, right? All of those details are hidden away from me. And I have a plain language to indicate to the object what I want it to do. Decay yourself by 1 year. Right? Decay yourself by 1 month instead. Right? Just give it a different period. Right? The details of how it goes about doing that are encapsulated inside the object. We've seen this before. In fact, you've seen this before in even C. Math.square root of 2. How does it work? Did you ever ask yourself how it works? Eventually, if you take a systems course, you might have to actually implement it. So then you'll have to answer that question. But did you ever ask yourself? Probably not. Did you ever ask yourself how those buttons on your calculator work? Probably not. You just like the calculator gave you the answer, right? In other words, the answer should be, who cares? It just works. Now, if you really want to know what it looks like, we can follow it and go ahead and go to compute. There it is, right? About 100 lines of code, complex bit masks and shifts and stuff like that, right? All the way down. How many lines of code is that? 1,614, and we started on what? 1,500. So 114 lines of code to do the square root function, right? Did you ever really care about those 114 lines of code? Nope. That's called abstraction. The details, which there are lots of details here, are abstracted away from us. We don't have to worry about it. Right? Another example that you've seen, local date, right? Foo. How does local date represent a date? Is it an ISO 8601 string? Is it a Unix epoch number? Is it 3 numbers? Year, day, and month. Right? Again, what's the answer? Who cares? Right? The way that it represents a concept is inside the class. We don't have to worry about those details. That's abstraction. And we all know, of course, that it is 3 numbers. Year, month, and day. Right? But we don't care. So now I'll ask the question, how does an isotope decay itself by a period? Who cares? It's in the class. We don't have to worry about it. Unless we, of course, have to write the class, and then we do have to worry about those details. Right? 4 lines of code. That's a sufficient amount of details that we want to put it in the class and not have to worry about it ever again. Of course, it needs to work. So let's see if it actually works. Right? Do we get the same answer as before? Yes. But this is much, much cleaner code here. Right? Right? Do you have to worry about any of those details here? Not at all, because it's inside the class. Okay. All right. So, what else do we want to do here? Oh yeah. How could we make this function a little bit more, I don't know, functional? Right? Right now we're returning nothing. What could we return? So we had 10 grams, and we decayed it by 1 year, and now it's 9.76 grams. Right? What else would you? What other information could we communicate to you if you wanted it? How much it decayed? Right? So we could return a double. Right? Decays this isotope by the given period and returns the mass that was decayed as a result. Right? So for that, I'm going to say new mass, double new mass, is equal to this dot mass, and then I'll say double mass lost is equal to this mass minus the new mass, and then I'll say this dot mass is equal to the new mass, and then I can return the mass that was lost. Okay? Does my code over here have to change at all? No, you can call the square root function then and ignore the result if you want to, right? Or you can go ahead and capture that value. Mass lost is equal to that. I'm not going to use it, but that's a way that we have, you know, improved the functionality of this. Right? Anytime you have a void function, think, could I make it more functional by, or could I make it more useful by returning something instead? Okay? All right. How else could we improve this? All right. I now have, okay, what if it were twice as large or massive? All right. That is, I want to compare the decay of 2 samples of strontium-90. Right? So what I want to do is I want to create a new mass here, or a new isotope. What I'll do is I'll come back up here and I'll call this isotope sample A. That's going to break all my code, right? So let's do it properly. Right click, refactor, rename, and then you can rename it everywhere else. Oh, sorry, isotope sample A. There. Okay. What if I had another sample, sample B? Isotope sample B is equal to new isotope. It's going to be the same but with a different mass. So it's going to be isotope sample A's name, so dot get name, dot get, was it half-life mass or was it mass half-life? What was the order? Half-life and then mass. So there's the half-life, and then the new mass here will be, say, 20 kilograms or 20 grams. Okay? That was a really long line, wasn't it? Let me go ahead and move it down to the next line. Is there a way that we can improve this? Right. Basically, I want to construct a brand new isotope that is kind of a copy of that other isotope over there. Right. That's called a copy constructor. Right. So let me go ahead and create, and you're not going to be able to generate code for this because it's not supported up here in the constructor using fields, right? So I don't think it is, at least. Yeah, it's not. Okay. So let's go ahead and create a public isotope that takes an isotope, right? As well as maybe a mass, double mass. Okay. Now what I want to do is I want to copy over the name and the half-life, but not the mass. I'm going to be doing this mass right here. Okay? Let me steal that code there. Isotope.name and isotope.half-life. And this dot mass is equal to that mass up there. This is known as a copy constructor. And you don't need documentation on this either, but I'm going to put documentation in there because when I put it in the notes, I want you to remember that this is a copy constructor. Copy constructor that copies the name and half-life of the given isotope but with the new value for mass. Right? There. It's a way that I can make a partial copy of another object, but then at the same time change one of its values. Okay? We'll revisit that later on, but yeah.
Do you necessarily, this is sort of off topic, but do you need to write like your credentials on every single object that you create as well, or is that just kind of a given?
No, not your credentials, but it's something like this.
Okay.
Right? Yeah. Generally, you would only need an author header there wherever you put your main.
Okay.
Right. Yeah, and in fact, when we get to the project, you don't even have to do that because we require you to hand in a README file with your name and your partner's name if you have a partner. Right. Okay. All right. So there we go. And by the way, in real life, you'd write a script that goes in and auto generates copyright notices on everything so that you're not repeating it. And also, now it's 2025. I'll run that script again, and now it's copyright 2025 instead, or the copyright for the last time you changed something in it, right? So in real life, you would automate that entire process. All right. So that's a copy constructor. It allows you to create a copy. We've seen this before, by the way. Do you remember? We can create a list of integers. Numbers is equal to new array list of integers. Right? And let me go ahead and bring those two things in. Import that and import that. Right? And if you wanted to convert it over to a set of integers, in other words, you wanted to get rid of duplicates, right? Unique values is equal to new hash set of integers. You can omit that, by the way. Here's a 50-cent word for the day. Do you know what an elide is? Or elision? Right? We do it in language all the time, where you omit syllables, right? Did you, right? Did you go to lunch today, right? You elide things away. You can also elide things in code, right? It's not necessary to put that second parameterization there. But here is a copy constructor. If I wanted to take these numbers and convert them over to a set, I can go ahead and pass this list over into this set. Likewise, I could do the same thing with another list. Right? Numbers copy is equal to numbers. Right? Let me show you the consequences of that. Numbers.add 10, 20, and 30. 20 and 30. Right? And let's print out, then what I'll do is I'll say numbers copy dot add 42. Hopefully you covered shallow and deep copies in CS1, but if not, let's review, or either way, let's review. Println numbers and numbers copy. Now before I run this, guess, what is this going to print right here? Remember that I added 10, 20, and 30. Right? Then I copied them all into the numbers. Then I added to the copy 42. So what values will be in the original array list? 10, 20, and 30? Yes? What about, why will 42 be in there too? No, because it was added to the deep copy of that. So what numbers will be in this? 10, 20, and 30. It was copied over on this line right here, and then we added 42 to it. See? They're two completely different copies, but this was initially it was a copy of this thing up here, right? of this original numbers here. So copy constructors, very, very useful things. Copy constructors are very useful. So remember that for your, not for your first assignment, by the way, but for your first project. Right? We'll revisit that later on. Okay, as a reminder. But I'll leave that there in your code. Okay. Okay. So how do we update this code here now so that we don't have to have that really long line? I'm just simply going to pass in isotope sample A. There. Right. I didn't have to rip the guts open of the object and pull those two things out just so that I can hand them to another object. That object is doing my work for me. Right? And now let's go ahead and put it back onto one line. So object-oriented programming can lead to simpler code. Simpler code is more maintainable code, and it is less brittle code. Why is it less brittle? Simple. Keep it simple, right? Stupid, right? In engineering, you like things that are simple because there are fewer failure points, right? If you have this really, really complicated thing that does something, right, but it has like 10 different potential failure points, and then somebody else designed the same thing with the same functionality, but it only had, say, 2 failure points. Which one of those is the better design? The one with fewer failure points, right? So simpler code is usually better code, and you can get that through object-oriented programming, right? It's also better organized code, because where is isotope stuff? It's now in the isotope class, right? We've isolated everything to do with isotopes in the isotope class here. All this complicated stuff, right? All of this complicated stuff is now located inside the class, right? Okay, so let's start formalizing some of this. And again, I'll post that later, right? Okay, so the motivating introduction we gave isotope class, right? Demo, there we go. So a review, Java is a class-based object-oriented programming language. Oh, I can zoom in here, sorry. There you go. And simply that means that everything in Java is a class or belongs to a class, okay? There are what should I call them? Non-class-based object-oriented programming languages. JavaScript is a classic example. It was object-oriented, or it had some object-oriented programming principles, but it never had classes until like 10 years ago. And the reason that they added classes was because that is the de facto way of doing objects, right? You look at any language and its evolution. Some languages start out without classes and eventually they get them. Why? Because it's such a great concept. It's such an easy concept to get, right? Python, PHP, they eventually had classes added to them, right? Even though they're not really object-oriented programming. But as far as Java is concerned, a class models a real-world object or idea. We call these things entities, right? Okay. Classes allow for, this is wrong, but let me change this, for strong encapsulation, right? Strong encapsulation are 3 things which I've mentioned before. The grouping of data, we've got that over here in the isotope class. We've grouped 3 things together, all together into one logical unit. 2, the grouping of behavior, that is methods, functions, or functionality that act on that data. Do we have anything like that here? Decay. It acts on the data, right? It processes the data inside of that class. It processes the mass, the half-life, in order to create the new mass and decay itself, right? 3, it's the protection of that data, right? So that I am making this stuff private, so you can't access it except through these getter methods. And even if I did have a setter method, public void set mass, right? Even if I did have something like that, by putting it into a setter, I don't have the advantage of doing the following. If, let me go ahead and grab double mass, right? Mass, there we go, right? If mass is less than 0, right? That is bad code, right? You should not have set the mass to something negative. I'm going to throw an exception at you. Throw new runtime exception. Mass cannot be negative. Right? I'm able to control bad data through the setters. Right? Now, this isn't something that you would normally, that I would say that you should do. Generally, you don't want setters at all. You'd prefer immutable objects. But I will leave it in there as an example. Okay? In fact, let's make this a little bit more robust. I'm going to put final in front of this thing. Have you ever seen the final keyword in Java? Yeah? What does it mean? You've seen it in C. Const double pi 3.14159. Right? Should you be able to change pi? No. So what do? You make it into a constant. Right? We don't have the const keyword in Java, instead it's final. Likewise, oops, sorry. Likewise, I don't ever want you to change the half-life, so I'll make that final. With my current design, can I make mass final? What if I did? Can I decay it then? Nope. Right. So maybe you have an argument for not making that final. There are ways that you can make it final, right? For example, you could decay something, and instead of returning the decay product, you could return a new isotope that is decayed by that much, right? We might do that as as another demonstration later on. But otherwise, there's the protection of data. Make it private, right? Generally speaking, book things belong in the book class, person things belong in the person class, etc. Just keep repeating that over and over to yourself when you're designing your stuff, right? That you should not put one thing into a different class, right? You should not have, you should avoid, we'll talk about the anti-patterns later on, but there's something called the God class. What if you only had one class, right, for your entire project? Right? It knows everything, it sees everything, it is everything. It's God, right? It's the God class. That's an anti-pattern. It's something that you should not do, okay? You should generally speaking, you should have one class per entity, right? Or thing, right? You should protect your variables by making them private unless there is a very good reason, and note that I've put capitals on each one of those, a very good reason not to, right? And I think we had a very good reason not to in the isotope class, because we wanted to decay it, right? But otherwise, there was no good reason to ever change the name of an isotope. There's no good reason to ever change the half-life of an isotope, because the fundamental laws of the universe aren't changing anytime soon, right? All right. So make them private unless there's a very good reason to do so. Generally, you should look for ways to use composition, right? Composition is that a class is composed of other classes, right? An example, a book class owns an instance of a person class, the author, right? It's composed of an author, among other things, right? And variables, of course, right? So use composition. You break an object down into its constituent parts until, oh, that's a double. Oh, that's a string, which, by the way, a string is a class. So you've got composition right there, right? Oh, no, that first name, last name, well, that's a person. So let's create another class, right? Isotope has three things. There's nothing else there, okay? All right. So more formally, objects, right? What are objects? Well, they have three things, like I already just said in Java, but they have the one thing that I didn't mention is identity. That is an aspect of the object that distinguishes it from all of the instances. Do you remember when we were doing the book demo? Let me go back to that book demo, right? Do you remember that we had a problem with our last thing where we had like Frank L. Baum 5 times for each one of his 5 books? What I wanted was Frank L. Baum once for his 5 books. We did that, right? And we had, the problem was we didn't have identity. We solved that by coming over here to the person class and defining the equals method. That person is the same thing as that person if their first names match and their last names match, right? So there's identity as far as an object goes. We also have state, that is a collection of variables, of properties, elements, attributes, data, fields. We'll call them member variables. Right? When you created structs in C, what did you call them? Like if I had a struct in C with an integer, a double, and a char, what was it? What would you call those? Did you call them member? You did structures, right? Structs? Okay. So you called those member variables? We'll call them member variables too. Right? Then finally, it has behavior. The functionality, in other words, methods, of the object that does or the surfaces it provides. Basically, the public methods in the object. right? Okay, that's what that means, behavior. So when we look at your designs and your design document, which we'll be talking about next week, right, we're going to ask you, well, what's the behavior of this object, right? In other words, what methods do you plan on putting into that object to support the program, to support the project, okay? All right. This is kind of important, but I'm not going to dwell on it. Communication between objects are done via message sending, right? You'll see that all over the place in object-oriented programming books and stuff like that. What does it mean? Here's the message sending. That's it. It just means that you're calling a function, right? In other words, I'm sending a message to decay yourself by 1 year to this isotope sample A, right? All you're doing is calling functions, right? So in other words, you call or invoke a function, or method, I should say, method of the class, right? Okay? So nothing fancy there, but they like to come up with fancy terms, right? All right? This is, I could come up, there's plenty of terms like that, okay, we've had the same thing now for 100 years. We need to reinvent it. We'll call it something else. Now it's something new, right? So, like, you know all hashtags, right? Hashtag, you put a hashtag in social media, right? And it's indexable and searchable. You know what that's from? Have you ever heard of IRC? Internet Relay Chat? Back to the 60s and 70s? That's where it comes from, right? It's nothing new, right? Social media might be new in that everybody uses it, but you know, geeks were using that back in the 60s and 70s to talk to each other and debate about Star Trek or something, right? All right, so again, communication is facilitated through the public interface, right? And then finally, otherwise, all aspects of an object are hidden, right? We call this information hiding abstraction. I already gave you an example of it. Local date, how does it represent a date? I don't know, I don't care. It's hidden away from me. This is abstraction, right? It's information hiding. Right? We don't want to have to worry about the representation, nor the implementation of an object. We just want to use it, right? That's it, okay? All right, so let's see. Yeah, let me go ahead and introduce the 4 pillars, and then we'll go ahead and take it up next week. The 4 pillars, 2 of them we've already seen, abstraction and encapsulation. But then we're going to look at inheritance and polymorphism. And again, like I said, we've already seen abstraction, so no need to look at that again, but I will enumerate everything that we just did. It's a form of information hiding. How does square root work? Who cares? It just does. That's called procedural abstraction. This is a function, it's a procedure. A procedure is another name for a function. And so how does it actually work? It just does. We hide those details so we don't have to worry about it. How does local date represent a date? 3 integers, we know the answer there. A single ISO 8601 string, a single number as an epoch time. Again, who cares, right? We just want to use it. Who cares? We just want to use it. Now we do care if we have to actually implement it, right? But then once we've implemented it, we never have to worry about that again. But it relieves you of the need of knowing any details of the object. And then finally, encapsulation. I think that we've already done that, but I'll go ahead and repeat it since I've got it in the notes here. It's the grouping of data that acts on one logical unit, the protection of that data, and the grouping of methods that act on that data. Do not break encapsulation by locating data or methods outside of a class that it belongs, right? Like we did over here. I no longer have the original, I should have saved the original so that we can compare and contrast. But when all 3 of these variables were located outside the class, when all the behavior for this decay function was located outside of the class, that's breaking encapsulation. Don't break encapsulation. Right? Bank stuff belongs in the bank class. Person stuff belongs in the person class. Right? Good abstraction and good encapsulation, those work together. And the final thing that I'll note before we go up to lab today is make sure your modeling is correct. Right? Modeling is correct. Right? Is a person a string? Burke, comma, Chris. Is that who I am? Am I a string? No. What would be a person? Am I a social security number? I'm not going to say what it is. I'll say my name, but not my social security number, especially on a live stream. Right? So, am I a string? No. What am I? I'm a person. Right? So that what does that tell you to do? Create a person class. Right? What about an address? Is an address a string? Now, what is an address? Street, city, state, zip. Right? Maybe 2 streets there. Right? Maybe an extended zip code. Right? If you have more than one thing on your hand, right, what does that tell you to do? Create an object. Use encapsulation. Use proper modeling. Right? Address. There we go. Okay. All right. So assignment 1 is due Friday, tomorrow by midnight. Lab 3 is due tonight by midnight. After that marks the end of the introduction to Java. And what we'll do next week, starting next week, is your big project. Right. So I'll post a new post about following along with the Gantt chart for the project. But on Tuesday, what we'll do is a standalone lecture on technical writing. I wish I could get somebody from the Writing Center. There is a UNO Writing Center, by the way. I wish I could get somebody from the UNO Writing Center to come down, because that's what we do in Lincoln. And they help me out with it because we're going to have a couple of exercises. Exercises that are really, really useful, actually, to address writer's block, to address, getting started on certain stuff. And we're going to talk about what technical writing is. Because 1 week from this Friday is your first draft of your design document. First draft, right? It's not going to be good. It's not going to be complete. Your final design document is probably going to be 10 pages or so. Most of it's going to be figures, right? The first draft does not have to be 10 pages. It should not be 10 pages. It should probably be the introduction and an overview of your design, right? Because you're going to go back and you're going to iterate on that. It'll also be the design for the first phase, right? You're going to tell us what classes are you going to make, what are the property, the member variables that you're going to put in those classes. Because if it's wrong, we're going to tell you about it, right? And you'll get full points for the drafts as long as you're putting forth a full effort. But that design draft is your opportunity to get feedback on your design. We're going to know that design sucks, or that's going to lose a lot of points because of X, Y, Z. A person is not an address. An address is not a person. Reminders of things like that. And so the more work that you put into it, the more feedback we can give, right? So, but we're not expecting, that's all. You've got 5 drafts, and then the final draft. The final draft is what we grade, right? There are points along the way, but that's based on basically completion. Okay? And we'll talk more about that on Tuesday then. Otherwise, focus on Lab 3, Assignment 0. Right? All right. I'll see you.